All right, let's get right into this. Back in 2019, something happened that really shook the world of computing. A team of researchers announced they had built a machine that did something so complex, it basically redrew the map of what we thought was possible. This is the story of quantum supremacy. So, to really get a handle on just how big a deal this was, let's start with a number: 10,000 years. Yeah, according to the research paper, that's how long it would take the most powerful supercomputer on the planet at the time to solve one very, very specific problem. And then came this, a totally new kind of processor called Sycamore that did the exact same task in just 200 seconds. Seriously, let that sink in. A 10,000-year marathon for a classical supercomputer was a 3-minute sprint for this quantum machine. The difference is just, it's unbelievable. Now, this incredible leap in speed is what scientists call quantum supremacy. It's a massive milestone for sure, but the name itself can sound a little intense. So, what does it really mean? Let's break it down. That word supremacy, it's a bit misleading. This isn't about quantum computers suddenly being better at everything. They're not. Your laptop is still way, way better at checking your email. So if it's not about being better at everything, what's the specific achievement here that actually matters? So quantum supremacy is that very specific moment, that tipping point, where a quantum computer solves a problem that is for all practical purposes impossible for any classical computer. And the key phrase here is in any reasonable amount of time. 10,000 years? Yeah, that's definitely not reasonable. And this quote from the paper really gets to the heart of why this whole experiment was so important. It wasn't just about setting a speed record. It was proof of concept. It showed that all these wild theoretical ideas about quantum computing could actually be built, and that there weren't some hidden laws of physics that were going to stop us. Okay, so we've got the concept down. But what about the machine itself? Let's take a look inside Sycamore, the quantum processor that made it all happen. So this is it, Sycamore. It's not a computer like you'd have on your desk. Think of it more as a highly specialized programmable processor that's been designed from the ground up to tap into the strange and wonderful rules of quantum mechanics. So how does this thing even work? Well, Sycamore runs on 53 quantum bits, or qubits. But here's the wild part. To get these incredibly delicate qubits to do their quantum thing, you have to create this extreme environment. We're talking colder than deep space. Just a tiny sliver of a degree above absolute zero. I mean, the engineering that goes into that is just mind-boggling. In controlling that fragile quantum state, it takes an insane amount of precision. The whole system uses 277 high-speed converters that are zapping these perfectly timed microwave pulses to nudge the qubits around. It's really like trying to conduct a massive orchestra, but at the atomic level. All right, we've met the machine. Now, let's dig into the impossible task that it was built to solve. This is a really important point. The problem they chose wasn't a practical one, like, say, cracking encryption. Instead, the researchers were really clever. They designed a special benchmark task, a problem that's perfectly suited to a quantum computer's strengths and a classical computer's weaknesses. Why? Because a classical computer has to calculate every single possibility one by one, and that's a number so big it's hard to imagine. But a quantum computer, it can explore all those possibilities at the same time. So the task was basically to predict the most likely outcome from a random quantum circuit. The paper uses a great analogy for this. Think about shining a laser through a piece of frosted glass. You get that speckled pattern of light, right? Some spots are bright, some are dark. Sycamore's job was to predict where the bright spots would be in a gigantic 53-qubit version of that same problem. So here's how they did it, step by step. First, they entangle all 53 qubits, which is this cool quantum trick that links their fates together in this really complex web. Then, they run a random series of operations on them, kind of like shuffling a quantum deck of cards. After that shuffle, they measure the result, which spits out a string of 53 ones and zeros. But here's the crucial part. They do this whole thing over and over again, millions of times. It's like rolling a pair of dice again and again to figure out which numbers pop up most often. This process reveals the most probable outcomes of their quantum circuit. Okay, so that brings us to a huge question. If the problem is too hard for a normal computer to solve in the first place, how on earth do you check if the quantum computer got the right answer? It's not like you can just look in the back of the book, right? Well, their solution was really smart. They couldn't directly check the final, full-blown 53-qubit answer. So what they did instead was test Sycamore on simpler versions of the same problem, versions a classical computer could still handle. It's kind of like checking a student's work on basic algebra before you trust them to do advanced calculus. They compared Sycamore's answers on the easy problems with the known correct answers, and guess what? It passed with flying colors. And here's the proof in the pudding. As you can see, for every single simplified test they could run and actually verify, Sycamore's real-world performance perfectly matched what the theory said it should do. Because it was so reliable on the problems they could check, they could be super confident it was also working correctly on the monster problem that they couldn't. So, the experiment was a huge success, the claim was solid. But this is where it gets really interesting. What does a milestone like this actually mean for the future of computing? Well, the biggest takeaway is this. It was the hello world moment for a brand new type of computation. For the very first time, a task was completed that, practically speaking, could only be done on a quantum processor. And this achievement kicked off what experts now call the NISQ era. That stands for Noisy Intermediate Scale Quantum. It basically means we now have quantum computers that are powerful, but they're not perfect yet. They're still noisy, they still make errors, but they're already capable of doing some pretty amazing things. This timeline really puts it all into perspective. The whole idea of a quantum computer was first floated by the physicist Richard Feynman way back in the 1980s. It took almost 4 decades of incredible, painstaking research and engineering to get to this moment in 2019. And the journey is far from over. The next huge goal is building fault-tolerant quantum computers, machines that are stable enough to run algorithms that could literally change the world. And even though we're still in this noisy era, the paper points to some really exciting applications that aren't too far off. These NISQ processors could totally revolutionize fields like material science and drug discovery, solve unbelievably complex optimization problems, and maybe even give machine learning a massive boost. But maybe the most profound thing to come out of all this is theoretical. For decades, there's been this core belief in computer science called the extended Church-Turing thesis. It basically says that any problem that can be solved efficiently on any kind of computer can also be solved efficiently on a regular one. Well, this experiment provides the first real-world evidence that this foundational idea might actually be wrong. It suggests there's a whole new class of problems out there that are just fundamentally beyond the reach of classical computers, no matter how powerful we make them. The paper ends by leaving us with this really powerful and exciting question. We've shown this new kind of computational power exists, so now the race is on to find the killer app. We're really standing at the dawn of a new age in computing, and the most incredible discoveries might be just around the corner. What do you think they'll be?